When a synthetic neuron in a language model receives a word, it outputs a number. This is what's called the activation value of the neuron for that word. This activation value is the result of the neuron's processing of the word. In other words, it's the way the neuron translates the word. But what is the semantic meaning of this value? Do different activation values correspond for a given neuron to different semantic meanings? What semantic significance is carried by low, medium, or high activation values? What purpose does the activation value serve for the neuron? Does it seek out particular values that carry specific semantic functions? How does a neuron use activation values to locate and focus its attention on semantic regions it is specifically looking to detect? We explored these questions within the first two feed-forward layers of OpenAI's GPT-2 XL, involving a total of 12,800 neurons. We focused on the top 100 words that each neuron responds to most strongly on average. 2 studies were conducted, each using a method that takes the opposite approach of the other to offer different empirical angles on the phenomenon we were examining. In our first study, we divided each neuron's responses into 5 categorical clusters, that is, 5 semantic themes to which the neuron is particularly responsive. For example, for one neuron associated with sports-related nouns, we identified the themes, team names, player names, manager names, stadium names, and competition names. For another neuron tied to the concept of optical phenomena, we found semantic clusters such as light and radiation, optical and light phenomena, optical devices, visual effects, and environmental factors. The question we asked was, for a given neuron, do the words in these different semantic clusters produce significantly different activation values? In other words, is there an ordered relationship between the average activation values of these different semantic themes? This would suggest that activation values encode semantic meaning, that a word's level of activation is linked to a particular semantic significance. 2 main findings emerged. For categorical clusters associated with moderately high activation values, there were no significant differences in activation between the clusters. In other words, medium activation values do not appear to encode semantic distinctions. We termed this activational indifferentiation. Conversely, when at least one of the categorical clusters showed a very high average activation value, more distinct activation differences were observed between clusters. These very high activations appear to carry semantic information. We call this activational differentiation. In the second study, we first isolated several homogeneous activation segments for each neuron, based on the words it responds to. We then grouped the words corresponding to each of these segments and measured the internal semantic similarity within each group. Again, 2 types of results emerged. The word groups generally displayed low semantic coherence. However, the higher the average activation value of a segment, the more semantically coherent the corresponding group, even though the increase was slight. We refer to this phenomenon as categorical homogeneity. Our findings suggest the existence of intra-neuronal attention, a phenomenon characterized by no significant relationship between activation zones and semantic zones for words with medium activation levels, a subtle but consistent relationship between activation zones and semantic zones for words with very high activation levels. In other words, activation serves as an intra-neuronal attentional vector. It allows a neuron to identify and isolate, among the many words it responds to, a subset of words specifically tied to very high activation values. These words are relatively more semantically similar to one another and constitute a distinct categorical segment that holds specific interest for the neuron. This form of intraneuronal attention is closely linked to mechanisms of vigilance and selective attention. In human psychology, conceptualization, renner in the sense defined by Gerard Verneau, refers to identifying the crucial features of objects, in our case, words, that a cognitive system must act upon in order to function effectively. Conceptualization is an attentional process in that it enables selective focus on a limited set of important object features to align action with their critical properties. An artificial neuron can thus be viewed as a synthetic cognitive agent of conceptualization whose function is to selectively attend to a specific subset of words within the broader set it responds to. This subset becomes the set of words that belong to the neuron's critical in-act concept. the category the neuron is responsible for detecting and selecting in order to support efficient language processing. For each neuron, its critical in-act concept is formed by the words that elicit very high activation levels. These particular words, marked by activational differentiation, tend to converge semantically toward a relevant categorical feature for the neuron. We describe this as categorical homogeneity. Conceptualization and intra-neuronal attention, taking place within a layer in neuron, are thus foundational synthetic processes. They pave the way at the next layer, N+1, for the formation of new thought categories, more functional ones, suited to the neural network's assigned tasks for which it was trained. In this study, we investigated the extent to which perceptron-type neurons in language models exhibit a synthetic process of conceptualization and intra-neuronal attention, a process that allows each neuron to identify and isolate a specific categorical subsegment within the artificial thought category it represents based on its activation space. We asked whether formal neurons internally encode a relationship between activation segmentation and semantic segmentation. This relationship appears to exist, though only partially, and only for words that elicit very high activation levels. Intraneuronal attention delineates, within a given neuron in layer N, an activation zone tied to a specific in-act neuronal concept, a synthetic concept from which categorical restructuring processes can then unfold in neurons of layer N+1, driving the emergence of higher-level categorical abstractions that define the thought categories of these superordinate neurons. Thank you for joining us on this exploration of synthetic thought in artificial intelligence. You can find the article mentioned in the video, as well as all the work from Neocognition Lab on neocognition.org. See you soon for a new video.